Our next speaker is Derek Webb. He's in the room. Derek is the CEO of the company Biorem. He has knowledge on gas and air abatement solutions, having been directly involved in the design, manufacture, and management of over 2,000 installations. Quite impressive. His extensive theoretical and practical knowledge has been instrumental with the successful completion of a wide spectrum of industrial and municipal projects handled over these 20 years of career at Biorem. He's currently serving as a director on the board of Ontario's Environment Industry Association and as a director of the Green Centre. So his talk is about navigating the complex landscape of biological odor control solution for waste water application. Thank you, Derek. The floor is yours.
And good morning, everyone. It's a pleasure to be here. You know, it's been a long 18 months, so it's actually nice to actually see people in person and exchange ideas. This is long overdue. So I've got a lot to cover today, so I won't spend a lot of time talking about my company. We're a public company. We've been doing this for 30 years. By the end of this year, we should finish our 2,100th installation, and these are just biological installations. So what we've tried to do is take the experience from these installations and culminate it in a high-level, easy-to-digest format so that you can have a better understanding of how complex selecting a biological system is. All right, so when we look at trying to come up with the optimum solution, I always say go back to first principles. And this slide is just really trying to give you that pathway of how to get there. So you always go back to the first principles. You know, what are the upstream physical processes? Not every single wastewater application is the same. So understanding the emission sources, understanding the catchment area, what type of wastewater is coming into the facility, all have an impact on what the gaseous phase emissions will be. So certainly airstream characterization and quantification is critical if you want to optimize the solution. The next kind of bucket that we start to look at is really the facility location itself. You know, part of that is the regulation. Whether you're trying to achieve a 1 odor unit, as Anna was explaining in her keynote address this morning, is very different from trying to address a 5 or a 10 odor unit situation at the nearest sensitive receptor. So the proximity of those neighbors has an impact on the solution that you may look at. Aesthetics is becoming increasingly important as we move forward. You've got urban encroachment, you have critical infrastructure being placed directly next to residences, between parks, golf courses. You need it to look good as well as to perform. And then obviously dealing with utilities, you know, most wastewater facilities, you don't have an issue with water consumption or wastewater consumption, but that is becoming an issue, and certainly energy conservation is becoming a bigger and bigger topic. Any evaluation has to look at the economics, right? CapEx, OpEx. You know, it's a little frustrating as a businessman when I look at, you know, it's 2021, and there still seems to be a lot of focus on the initial capital expense rather than the long-term cost to the facility over the life of that piece of equipment. So a lot of lip service is being paid, but not a lot of action to actually institute cost savings over the life of a project. So, and then as part of the economic evaluation, a lot of cases actually you should be looking at other technologies as well. So don't just focus on the biological. The economics may dictate that other technologies may be more suitable for that particular application. Getting all this information, we can combine it together, set up a criteria table, and then hopefully pair the optimum solution for that application. So this next few slides kind of spend a little bit of time to explore the complexity of just the technical aspects of the biological solutions. So many of you have heard of biotrickling filters, you've heard of bioscrubbers, you've heard of biofilters. I think in the industry, unfortunately, the term biotrickling and bioscrubbing is erroneously used interchangeably. They're actually quite different types of reactors, and they're used for very different applications. So a biotrickling filter and a biofilter are examples of fixed film bioreactors, right? We immobilize bacteria on the surface of some type of packing. whereas a bioscrubber is more like a traditional wastewater system, right? The bacteria are freely suspended in that recirculating fluid. So what you have is a mass transfer tower and a little small wastewater reactor. Why is that important? Well, it depends on the compounds that you're trying to treat. So there can be many different types of configurations of all these technologies, whether they're once through with a pH gradient through the trickler, recirculated. You can have countercurrent where the air and the water are going in opposite directions. You can have them going co-current, and you can even design some of these systems to go horizontal flow as well. All of these factors come into play when you're dealing with certain site locations or certain compounds that you're trying to get out. In terms of the types of media, I mean, we could spend a whole session just talking about the media. Every type of inert and consumable products out there, from engineered medias to I've seen natural products as mussel shells being used as a trickler substrate. And then just to make things a little easier as well, I've kind of put the list of some of the compounds that you would most commonly see treated by each of these technologies. So the bioscrubber is primarily used for high VOC concentrations that are highly water soluble, where you get a lot of biomass and you need to deal with it in an efficient manner. The trickling filters are typically best to deal with water soluble components. You can run them for low level VOCs, but those will be a very different system from one that has been built or designed to deal with hydrogen sulfide. And then a biofilter can give you a much wider range of compounds that can be treated just due to the nature of the media, the drier nature of it, and the wider range of microorganisms that you can grow. So when we look at the complexity, it gets even more complex, right? So now you've got to start looking at all the different sources. How do the sources differ? And as we start to get more advanced wastewater treatment facilities, with more treatment stages and more novel pieces of equipment, that has a direct impact on what could be in the gaseous phase as an emission. So for simplicity's sake, what we do is, taking the collection system and the waste coming into the facility out of the equation, let's just kind of look at wastewater treatment in three main areas. The collection system, and I kind of throw in headworks as part of that due to the composition of the gases. We can look at liquid phase treatment, and we can look at solid phase treatment. What you see is the primary odor constituent at the front end. So from the collection system all the way through to liquid phase, the dominant odor contributor is H2S. When it first comes into the plant, it'll be a higher concentration. As you move through the plant, you usually see a drop in those concentrations, but it's still the dominant form. And then you see the organic sulfur compounds being more of a secondary role. Now this all gets reversed at the back end of the plant when you're dealing with the solids treatment. In these cases, we tend to see nitrogen-bearing compounds like ammonia, amines tend to be the dominant with organic sulfurs, and then your secondary odor contributors could be hydrogen sulfide and VOCs. Now obviously the piece of equipment has a huge impact on that, and we'll touch that in the next slide or two. So why is this? I'm spending a lot of time talking about the different compounds, the different sources, and all these different biological reactors. Well, it's important because of how the biology behaves and because of gas-liquid interfaces and solubilities, molecular structures of these compounds. So some of the key design considerations when we look at these things, we look at some of the bacteria that remove certain components are different from the bacteria or fungus that take out other components. One of my colleagues yesterday was talking about ammonia as being one of those compounds that can be problematic in a biological reactor. So we've actually identified the two key ones we look at are hydrogen sulfide and ammonia. So ammonia, you will get a buildup of salts that will cause an issue with nutrient uptake with certain bacteria. You will eventually get to a situation where you can't take out the full range of compounds that you need to. Same thing happens with hydrogen sulfide in a biological reactor. So the bacteria that actually degrade those compounds end up producing sulfuric acid as one of their byproducts. The sulfuric acid drops the pH. Now you're in an acidic environment which is conducive to certain types of bacteria which remove the hydrogen sulfide, but your other beneficial organisms are impacted And so you can have a system that's doing 99.5% H2S removal and still have a fairly significant odor issue. So just some key markers. When you're dealing with the more complex sulfur compounds like DMS or DMDS, now you're dealing with a very complex molecular structure, you're dealing with low water solubility, so choosing the right technology to address those and having the length of time, the retention time, the time that the air stays in the reactor becomes important to get that full degradation. It's also critical because these compounds have extremely low detection thresholds. Looking at diurnal variations, also critical. If you have a facility that goes from 0 to 1,000 ppm, and this is changing throughout the day or the week, this also has a very unique application in terms of how you should design to deal with those. Bacteria cannot respond immediately to a change in concentration. And then finally, this is becoming a bigger issue as we see more and more thermal drying of biosolids, as we see aerobic fermentation. You can actually get significant VOCs coming off your processes, typically volatile fatty acids. And these things, it's like chocolate for bacteria. They just absolutely love it. They go out of control growing to feed on this. And they produce a substance known as EPS, which is extracellular polymeric substances. It's like a sugar. But it looks like slime, it's horrible, but what it does is it fills the pore spaces, you have high differential pressure, more energy cost, declining performance due to preferential flow paths. So all of these things are further considerations as we try to pick the optimum solution. I won't spend too much time on this slide, but this tries to give you some guidelines, and it's not meant to be definitive. Understanding what's in the air is very important for matching it up with your piece of equipment, but it's not the be-all and end-all. You have geometry, you have costs, you have a lot of other things. What this slide attempts to do is give you the sources, how the typical composition of that air may change, and what that means from a pure technology selection standpoint. Then finally, I'll wrap up the discussion here with just 3 very short case studies, how these knowledges were either applied or not applied on systems. So the first one for the city of Oviedo in Florida, this is a headwork surge tank. You would think, the primary odor constituent is hydrogen sulfide. A trickler should do the work for you. However, this is in a very affluent area with very close proximity to sensitive receptors. So the client opted to do a 2-stage system to get high levels of H2S removal with a biofilter to remove all of the other VOCs. And you can see very good performance on the reduced sulfur compounds as well as total odor removal. The second application, which is a dewatered biosolids bunker, was meant to store waste activated sludge. So you typically wouldn't have a lot of H2S. However, in this case, the client opted to go for a biotrickling filter, which, as we discussed, probably wouldn't be the first choice. In this case, during testing, not only was WAS in the tank, but there was some raw sludge, which you can see demonstrated in a higher H2S concentration. But what you see is great performance across the H2S and mercaptan, but very poor performance on DMS and DMDS, leaving a residual odor. And then finally, just an example of where you would definitely want to go with a more dry type application is where you're dealing with dewatering of biosolids, where here you would expect to have very low hydrogen sulfide, where your odor is really coming more from the nitrogen bearing or the reduced sulfurs. So I guess at that point, I kind of tried to get a whole bunch here in 10 minutes as a high level overview, but I'll certainly open up the floor if there's anyone that wants to get into a little bit more technical detail.
Okay. Thank you very much, Derek, for this nice overview. So we have only time for one question from the audience. Okay, I have just a very short question. Yeah, Derek? Oh, yes, just a very short question from my side. How do you cope with the removal of recalcitrant compounds? Do you use any bioaugmentation strategy?
Yes, depending on the recalcitrance of the compound, we will look at specific cultures. Typically, this is not something we find in wastewater because I think you have enough of the beneficial organisms in the air to begin with. It's really about creating the perfect conditions so that they can thrive. When we get into specific industrial applications, when you may be dealing with an aromatic, dealing with xylenes or some type of solvents, in that case we'll cultivate a bacterial culture or a fungal culture to directly address those compounds.
Okay, and I don't know if you know that there has been a lot of advances, no? Molecular biology techniques. I mean, have you ever implemented a monitoring of the populations in this system? Because there is in the market, inocula, new media with inoculum. Have you ever done a monitoring to know if these microorganisms
We have.
dominate?
We maintain our own labs to actually to enumerate the bacteria. That's one of the things we'll do certainly on biofilters. With tricklers, we're not quite there. We haven't developed the processes to give results that are useful. With a biofilter, it becomes a lot easier, and looking at the numbers of bacteria and types of bacteria you have is a key indicator for the health, and it can actually be used as a preventative measure. The last thing a client wants or a facility wants is to deal with a problem after it's occurred. So we're looking at predictive. So by counting and monitoring the types of colonies that we have growing, you can actually determine what the health is and predict what that future performance will be.
Okay. Thank you very much, Derek.
Great. Thank you.
So we move to the next speaker.